Hi everybody, I am Ferraro, a PhD student from the University of Modena and Reggio Emilia, Italy, thus an employee of Minerva Systems. Today I will talk about this joint project made in collaboration with Zero Days Labs from a spin-off of the University of Minho in Portugal and TII, a company from UAE. So in this project we want to increase the security of drones using CHERI. Well, why? Nowadays, drones are used for different kind of application, from civilian to military domain. Think about search and rescue operations, surveillance, and drones typically collect data from the different sensors that they have, GPS, camera. They need to process this data in real time, and they can also be remotely controlled or autonomous. Now, we focus on this framework for designing drone, which is PX4, and is built on top of NuttX, a real-time operating system. And PX4 usually uses a flat memory space, and we all know it's really unsecure. And so we want to use CHERI to increase and protect this flat memory space, but we also need to keep up with the real-time constraints. So let's see how it is the PX4 NuttX architecture usually. This I'm showing you the simulation hardware setup, which means essentially even the sensors are emulated on the platform. So we have our operating system, NuttX, we have different peripherals, we have libraries, we have the file system, application like the terminal, the shell, and then we have the PX4 layers on top. Here we have other libraries like drivers for defining a common API of different of the same sensor. We have a library for accessing the timer, library like perf that is used to evaluate performance of a function or a piece of code. And PX4 is designed follows a modular approach, which means that each functionality of the system of the drone is represented by a module. So we have different modules, like here sensors, emulated sensor. We have this sensors module that collects data, raw data from the sensors and filter them to clean them a bit. We have the extended common filter that collects data and localize the vehicle, the drone. Then we have the actuators and that essentially controls the motors of the drone. Another important module is the commander. This one does some health check of the drone and also allow me to arm the motor or not, depending on the condition of the drone. And to communicate with the ground base, we use, there is this Mavlink communication protocol. So having a task, so a process, for each module would be too expensive for a platform like a drone. And so PX4 uses this work queue concept that are essentially tasks in which multiple modules will be executed on top. But there are also modules that runs on a single task. In particular, Mavlink also spawn a thread. So to communicate, all of them use this publish-subscribe protocol called microhorb. So for example, the GPS is a publisher of this sensor GPS topic. I don't know if you are familiar with the ROS2, for example, but okay, it's really similar. And then we have the extended common filter that is a subscriber to this sensor GPS topic. Now again, everything is in flat memory space. There is a version of PX4 that supports the MMU made by the Unikey, a Finland company. And in that case, NuttX provides these syscall libraries to map the syscall for the user space. Now, with or without the MMU, there are common vulnerability exploits. In this case, for example, if we provide by sending a message of the trajectory that is which has a payload that is big enough, we can get a stack overflow. So why we use CHERI capabilities? There are different examples that demonstrate that capability-based approaches can protect real-world systems, like SL4 protected this DRPA drone from DEFCON hackers. And so if we bring capabilities directly to hardware, we can achieve a fine-grained memory protection. We all know this. So let's protect PX4 NuttX. We run our experiment on the CVA6 CHERI with the ISA V9 on FPGA. So again, we have our NuttX. Now NuttX must be CHERI aware. So we use NuttX in hybrid mode, and he is managing the capabilities during the context switch and the interrupt management. We still have some modules running in hybrid mode because we are doing a gradual porting of modules in pure capability mode. And then we, for the pure capability world, we follow a bit the work that has been done by the Imperial College London with CapVM. So we have this CHERI manager that will create compartments with capabilities in which I will execute my PX4 module. So CHERI manager is split in two phases. The first phase is the initialization phase. Here I first create the capabilities and allocate the memory, load the health file into the memory, and define the capabilities and boundaries of them. And second, we really spawn the task running inside the compartment. So as you can see, there is this trampoline library that is a derivation of the syscall library made during in the MMU based setup, and this is but instead of calling the syscall, it just do a CHERI based trampoline into the CHERI manager space, and that I will directly call the right function that I will need to call, like a write, for example. The second phase is an interactive phase, because sometimes I need to jump into the compartment again, into the module again. And so in this case, I can recall my CHERI manager and for accessing the perf library to print the results of the performance, and also into the main function again, because sometimes I need to change some parameters of the module. So we did a preliminary evaluation using mavlink over serial, and sending the message of ping, so to measure the end-to-end latency. So we are sending the message to the platform and are waiting for a reply, or at least a given timeout expires. So here the preliminary results. Here, as we can see on the x-axis, we have the timeout frequency, which means that the highest the frequency, the less I wait for sending in the other message. So, and we compare the result in hybrid. So we have NuttX in hybrid mode and mavlink running in native RISC-V, and in pure capability mode, where I have this CHERI with the CHERI manager and the compartments. So in most of the cases, the results are comparable. There is just this 40 hertz that has some strange behavior, and this I'm currently investigating it. But overall, the average overhead is about less than 1%. If we also consider 40 hertz is less than 3%. So to conclude, for future direction, we want to compare these results with also an MMU-based PX4 NuttX, especially for understanding the performance and compare, for example, the syscalls with the trampoline-like functions. We are doing this CVs and CWEs analysis on PX4 NuttX and similar operating system like Autopilot, for example. And when the hardware will be available, we will also see if we can see this drone flying, really fly, let's say. Thank you. So I will some time.
That's one question. Why didn't you do it pure kernels?
Because we want to keep the compatibility with the other compartment, the other modules, because we are not the only one developing it, and also because it was the easy way to achieve the application, to protect the application layer.
Hello. Is there a big difference between the software and the operating systems you run on drones and what you'd run on small satellites? I think it'd be very cool to have CHERI in space, don't you?
I honestly don't know. I don't really know. I know that PX4 can be used also for rover, for example.
Yeah.
But I don't know for
CHERI on
space.
Mars. Okay.